Thank you so much for the opportunity given to come and present what I did like in previous years. Then the talk is on turbulent flow for magnetohydrodynamic. And then in this talk, we'll be looking at these issues. And then the very important point here is analyzing the Kolmogorov spectral theory, and then which is about the decay of the turbulent energy over a range of wave numbers, generally in the spectrum. And the outline of the talk is this one, like introduction, and then I give some definitions, like which is not necessary in this part, for the sake of being organized definitions. Then we'll be taking 5 times and giving a priori estimate. And then I give the main result. And finally, the conclusion. I think I made a mistake over here, like this. The main result is not a subsection. It's a section by itself. And we conclude, and then I give a reference. And then the whole topic is understanding or studying the system of equations. Yeah, the system of equations given by this one here, equation number 1. And this is generally what we at least assume, that the MHD equation, system of MHD equations is governed by such type of, MHD flow is governed by the system of equations. And U stands for the velocity field, V stands for magnetic field, and then here pi stands for. And then we're considering when the external force acting on the magnetic and the velocity field is not equal to 0. That's for the sake of considering, like for making the idea of having a turbulent flow instead. It means that we consider the external force as the initial data where the turbulence is being generated. And then how here, 0 infinity, this is the time interval, and D, and now this whole work was considering 2 spatial domains. And one is the periodic spatial domain, which is torus, and an infinite torus, and I'm not in love with this. And then D here is the spatial domain. Otherwise, if it is not the torus, the periodic torus, and then it is R3. Now, here are some pictorial examples for turbulent flows. And the first example picture in here is an application by Leonardo da Vinci by about 1500. And he studied, like he observed turbulent flow as if there are kind of 2 types of motions involving in it. And one is the curly one, and the other one is those straight ones, are like a laminar component, or maybe we can say that this one is. And then this one is like an aerodynamic kind of turbulence that comes out when an airplane is landing. Oh, and this one is like an ordinary river flow, or like the kind of water current between. Right? And all these things are taken from Wikipedia. And this is an example of MHD flow. The previous ones are hydrodynamic flow, and these ones are MHD flow. This is the tuning system in the nuclear power plant, and this one is, these are quite very good examples for. And this one is this one. And when it comes to mathematical studies of turbulent flows, we may observe 3 types of approaches. And the first one is by analyzing the Lore's-Weak solution, as it was proposed or assumed by Lore in his original works in 1931 to 1934. We consider the weak solution as if it is maybe treated as turbulence. And the other one is analyzing the decay of the energy of the turbulent flow, which I recognize in which I mentioned as Kolmogorov theory. And then the last one is, which I'm interested in, is by studying the stochastic partial version. It's like we analyze the stochastic version of fluid flows, fluid models. For hydrodynamic one, we may consider stochastic Navier-Stokes equations, and for the MHD one, we consider hydrodynamic. In this particular talk, the point is to show the intersection or like the relation between the first two. We start with the Lorer-Weak solution, or we assume Lorer-Weak solutions, and then try to show that this Lorer-Weak solution actually satisfies Kolmogorov. Okay. Now, the motivation of this work is based on the very nice piece of work by Briac and Craig in 2012, and in which they show, or they try to show that Navier-Stokes weak solution for Navier-Stokes equations satisfy Kolmogorov. And then the Kolmogorov spectral theory says that in a range of, like, there exists a certain range of wave numbers. That range, the spectral energy or the energy of the turbulent fluid decays according to k raised to the power minus. Now, C naught and epsilon, these are constants. C naught is called Kolmogorov constant, and epsilon is the rate of energy. And the main finding is here we define the spectral energy for the MHD equation this way, and this satisfies Kolmogorov. In other words, there is an inertial range of wave numbers, which for this particular case we call it the inertial range, where the spectral energy of Lorer-Weak solution system 1 given by this satisfies Kolmogorov, which means the energy this decays in this range of wave numbers according to, or at least close. And then we further estimate the boundaries, like the inertial range, the maximum bound and the minimum bound of the inertial range. Okay. So now here we start by defining Lorer-Weak solution for the system given by considering like an irregular force or a non-homogeneous force F. F1 is the force over the velocity field, and then F2 is the magnitude. Satisfy these conditions. And then now for the conditions over here, we are interested in this one. And that the spaces in here, H sigma and L sigma, are defined accordingly. So the very important point for this definition is the energy estimate. For the calculation of this equality, like one may look at like several references. But the best example for me is that the work by Kanom and Miao. And this is the Kolmogorov theory with, and then apparently we have an equivalent, which is not equivalent, but a version of Kolmogorov spectral theory for Magnetohydrodynamics equation, which is due to creation and iteration of and Turbulent. Actually, these two, they came at the same time, almost close to the same time. And this one is a work done by these three individuals, and which apparently supports the theory of creation and iteration. And according to them, in the inertial range, the spectral energy of MHD system decays not according to this one, or proportional to k to the power minus 5 over 3, but rather it decays proportional. And then I try to look at the relation between like which one is actually mainly supported by literatures. For MHD systems, is it the relation called the theory or Kolmogorov theory? Then I looked at the work of Verma, statistical system for MHD equations, in 2004, very nice review. And then in there, it mentions that most of the work is done on the spectral energy theory, actually supports the work of Kolmogorov, the theory that the spectral energy decay will be less proportional to k to the power minus 5. 3 than K to the power. Therefore, now our point is to give like a rigorous mathematical proof to support like the theory of Kolmogorov. And so Kolmogorov theory is based on symmetric analysis and stuff. Then here is what you call the inertial range. So according to Kolmogorov's classification, the energy in the turbulent flow is divided into two scales, the largest scale and small scale. The largest scale, the energy or the scale of the eddies in the turbulent flow mostly depend on the topology of the boundary. And then in this smaller scale, the further subdivided this into dissipation subrange in the inertia. Okay. So here the inertial subrange, the behavior is mostly determined by the energy dissipation, and then here mostly determined by. So this is the inertial range. So our target is to find like particular specific formulation for LT here and L. Okay? So here are definitions. We define S as feature imbalances with this formula, and this is a ball centered at 0 as flag is R, and if this is other set like UV belongs to this set, F belongs. Now we also have a loader projector over here, which helps us to simplify to eliminate the equation of the equation 1, and its Fourier transform. We may also, without lose of generality, we assume that this quantity is bounded from right by certain negative function R in the presence of loops and numbers. Out of this one is in the presence of Fi, like when F1 and F2 are not equal to 0, and then this one of course depends on 0. And one can show that it actually depends on a kind of linear scale. Yeah. So now here we have. Now, before giving our preliminary results, now we have this MHD equation in the Fourier space. And what we do is we actually take the Fourier transform of the entire MHD system. And then now if we define this transform or operator over here with this higher bit, with this one, and then putting this in back, and then using the part the lower projector or the Fourier of the lower projector here is given by this one. The simplification leaves us and then now we are dealing with the entire other three. And therefore, at some point, we may end up with a question of where constant or where to find it. So what we do here is we divide the entire other three into smaller boxes. And then the dimension of the cube is whereas where we introduce a smooth cutoff function is defined by this one. Today is the smooth cutoff function or 2 here about k of the length 2 delta, so that this is part 1 on a cube of same center with side delta, which is half of the size of the original cube. And outside of this cube k. And then the support of chi k one can easily see is that is given by this one. Now, to use this property over here, we define modifying functions. Now we have this modifying function, which is given by the convolution of x chi and u, x3. And this one is also another, like we can say that this is the piece moment of the energy in the box QK. And this is about something like the HP estimate for the functions F1 and F2, the external forces, and which I'm going to relate it with the definition of the weak solution, like the smoothness condition we have. All right. So now we have two a priori estimates. And now the estimates are based on HP. This one is like, in this we have U squared plus V squared, remember? And then this one contains the smoothness condition over this. And then if this is okay, then if U initially satisfies this, then for all positive time t, this is the first. And the second a priori estimate is this one. This is like one may say that the time average of the energy in the capsule. And so if we have the supremum of EK at time t is equal to 0, which means this is on the data at time t is equal to 0, bounded by this value, and then for all t, this is true. And then R2 is defined by this formula over here, very long formula, and R5 at any time t is given by this F infinity. Now, to prove the estimates, we need actually two big lemmas. And the first lemma is states that if we have this, the bound over here, and if there exists a decreasing function R1 of t, such that this is true for all t in R plus, and delta less than this amount over here, and if this is equal to then for anything here we do have this difference. And then in the next lemma we're going to do this estimation with the difference over here for entire EP. Alright, so to prove this on the first lemma, this lemma, and then what do is we define E2. So E2 is given by x chi u square, and then the magnitude over this square. And then we know that in complex numbers, the square of the absolute value is nothing but is the product of the complex number and then conjugate. So here we have u, this value, the square of the absolute value, this value, this one. And then taking the derivative over that gives this, and we do have this value now. Now, when you take the derivative of this one, we apply product, and then that leaves. Now, we don't have the Fourier estimate for like the Fourier equation, the equivalence of the MHD system 1 and the Fourier response. And then from that equation, we drive for the Fourier of U and the Fourier of V. And then substitute this over here, and then what we get is this thing. Comes up to here, we have 8 integrals. And then now estimating the integrals, we have I1 plus I2, I1 and I2 are these two values. This is I1 and this one. Now, this is less than or equal to, like, to put these things together, what I did was I took the minimum of now eta and nu. And then when I do the negative, the minimum of the negative is obviously less than, sorry, greater than or equal to the negative of the sum of the negatives. Now At this point, one may consider like by certain scaling, like consider U indicator to be 1, and then there is no need of writing this minimum. And we estimated I3 with this one. We did nothing, but here we use the normal, like the usual folder in front of everything. And then, but we have this, and then this one is given in the condition. This one, not, but this one is, we take this one from the support of the function. And similarly, we bound I4, I5, I6, and I7. And this is less than or equal to this. And therefore, finally, this whole value, the derivative of the E squared, the energy capsule, or the amount of energy with the QK is less than or equal. And for this, over the squaring of the, like when we put everything together, we get a form of A plus B raised to the power n. Without we use Sarah inequality. The Sarah inequality says that the n-th power of the sum of n terms, or the alpha's power of the sum of n terms is less than or equal to certain constant times the sum of all the n-th powers. So the alpha's power of the sum, and again is greater than or equal to certain constant, which that constant can actually be particular dimension, and less than or equal to expanded by certain inequality says we have, if we have AI raised to the power alpha, where I runs from 1 to n, and this is less than or equal to the maximum of 1 and n raised to the power alpha minus 1, and the sum of AI to the power alpha I1 n. And this again is less than or equal to the minimum of 1 and same number n to the power alpha minus 1 times the sum of AI raised to the power alpha I1 n. So once applying this formula, and then we end up with a very reduced form A. Now, at this point, we define a ball of radius R1 by BR1 of the form this. BR1 is equal to set containing all the functional E, by that E is less than or equal to R1 over absolute value K. Now, if we take E to be E2 and the boundary of BR1, and which means that E2 of KT is equal to R1 over absolute value. And then this is the ball, and then we are taking a final point at that point, like, sorry, a point on the boundary of this ball, which is equal to given by this. Then we do have this half of d by dt of this is less than or equal to this value, and this is. Indeed, actually, this is exactly. Now, which implies that this derivative of the square over here is less than that. Which in turn implies this value, the derivative of E2 is less than that. The boundary we always get like a degree. And then this implies the ball of radius R1 over K is a kind of attracting set for the functional E2. Therefore, this is less than or equal to 0, then we do have E2 of KT is always less than R1 of K, and then this is the proof of that. And the second lemma is this one, general EP. So the proof goes the same way. Yeah. It's the same way now, except the fact that instead of differentiating E2 square, we rather differentiate EP greater to B. And we get this, we apply the same thing, and then we end up with this. Now, please look at those things over here, those apart from P minus. Now, we do have this, we get this, because the absolute value is equal to the square root of the product of a complex number and its conjugate. And then in that, we do get this value. And this is nothing, but this is the kind of estimate we solve in equation. And then at the end of the day, applying all those and putting them together, we get the estimate over here. And the piece power of P over here is less than or equal to this. We once again define say BR1 use the same notation. Like this is for simplicity. Like to avoid confusion. BR1 is equal to this, R1 over here. Now taking setting E to be EP, and then taking EP on the boundary, and then we get same argument, we get this one. Right? And then we get this to be less than 0. Now here we have the condition in here. This is less than or equal to condition given in the lemma. This implies that same argument we are one parameter. Therefore, this is less than this value implies that if KT is always less than R1T over R2. Then we come to the first, proving the first a priori estimate, and then everything goes to the end. Now, taking the supremum over P, now as we say, EP over here is uniformly bounded in variable P. Therefore, if you take the supremum over P, and then we get the result for. And for the second estimate, we have if square over here, which is take the partial of that, and then that actually leads us to this formula. And then now here, if we define IP square of KT, yeah, to be this value, which is the time integral over that, and then have IP over here. So when you do all these calculations and then all those lengthy computations, considering all those lengthy computations, we arrive at this quadratic form with IP equal to this interval, the time interval. And then now this is the quadratic which is less than or equal to 0, and the leading coefficient is positive. And then if we solve this quadratic equation for IP, what we get is this one. This one. We just apply general quadratic. But what we know is the root IPKT, the whole statement over here less than or equal to 0, the maximum root for the quadratic equation over here is less than or equal to this value. There's an upward parabola, and then the stuff needs to be the parabola. The whole quadratic equation needs to be below the x-axis, and therefore, if it intersects the x-axis up there, it's going to intersect this point from the right. So this is the maximum possible. And now we say this, and then let P to infinite, and then that will be. Now this is our main result. Now we can bound the spectral energy function. So the spectral energy function is when the i's are 0, and then like we usually don't see the i. Because this t comes from r of t, where u squared plus b squared is bounded from above by r of t. So we have And then if this is okay, the whole is for all k in the T, either when Fy not equal to 0, and then this one R1 atmosphere. Now, for this, we define this one. This is the surface integral over there. And then we know this square, it is less than or equal to R1 square over K2, as it belongs to the set K R1 over K, R0. And then we know the surface, like the volume of this is a sphere of 1 radius of K, which is equal to 4 pi R square. So when you multiply that 4 pi R square, that the radius is also K. Now K square cancels out K square, and then we can then we use a similar argument with respect when Fy is different from 0. That's different, the time difference comes from the lower energy. Now we do have another estimate over here. Suppose that the initial data U naught V naught. Now this one is the time average of the energy, the spectral energy function. So we have this where R1 and R satisfy this condition, this relation. And then if Fy satisfies this smoothness, like this is the condition set by More, the definition. So the first slide. And the function, the spectral energy function satisfies the estimate. Which means the time average of a certain time interval 0 to t of E of kt is decays like is bounded from above by this. Now the important point is the exponent of k raised to the okay? The proof goes as follows, and then we bound this using EP, all right? And then we use the Fubini, and then we change the integrals over here. All right, the time average by estimate 2 is bounded by a value quite equivalent to this one. Okay? R2 square of 3 over this, and then we have 1 over 3 over here. And then there is this surface integral, and then we multiply that thing by 4 pi R square again. Okay, the force power is given by the K square that comes out with that. Then we do have it. Therefore, the time average of E is bounded from above by this value. And then to come to the bands on the inertia range. Now, assuming conditions in the previous theorem proving are true about Kolmogorov's inertia. So if you are talking about Kolmogorov's inertia range, we may assume that as an ideal condition, the spectral energy function satisfies Kolmogorov's theorem, which means it decays according to proportional to k to the power minus 5. So to prove this is like one of the simplest. So what we do is, now this one I need to say, okay, now the Kolmogorov parameters are like the stuff which appear in the Kolmogorov equation, they satisfy this. If this is not okay, and then the spectral energy is for that. And then here we have the K, if we are considering the interval K1 bar, K2 bar to be the inertia range, like K1 to be the lower bound, and K2 to be the upper bound. And then the inertia range is going to be K1, K2. So how do we do that? All right, and so this is the graph of the Kolmogorov function, spectral, like the Kolmogorov decay, C naught epsilon to the power 3 over K to the power minus 5. And then this one is the upper bound, this one will equal to that, and then we have another upper bound. And therefore, the inertial function over here is possibly satisfied, like the Kolmogorov spectral function can only be satisfied from this point up to this point, which we label this to be K1 and label this. So this region generally satisfies the bounds of the theorems, the previous theorems over here. So we have this one, this one has to be less than or equal to this. And then the time average, like if you're assuming, like if we are estimating the spectral function by its average, then what's going to happen is we may consider this to be equal to K of K as it is an average of it. And therefore, it has to be bounded from above by that. Therefore, this region, the child region, represents what we have in the previous. And then when you plot the Kolmogorov spectral function, if I name it that way, and then it intersects this region that satisfies the two bands only in this interval. And therefore, this has to be the lower band for the inertia range, and this has to be the upper band. Right? Now, if we keep narrowing this interval, and then if we assume that this is going to be equal to this one at some point, and then what's going to happen is this. The value at the left is going to be equal to the value at the right. Certain, maybe I did like a little bit of modification to write the equation. If this inequality changes its direction, which means K2 is going to be less than K1. And that implies that the spectral energy or the inertia range is going to be uninteresting. That doesn't make sense. Therefore, finally, in conclusion, the Kolmogorov spectral function or the Kolmogorov spectral theory is satisfied in the range K1, K2, where the value K1 over here is the lower band and K2 over here is upper band. And then in this range, it makes sense to consider that the spectral energy likely decays according to Kolmogorov. C naught epsilon raises to the power 2 over 3, K raises to the power 9. And the conclusion is Doris-Weig solution implies Kolmogorov dualism for the system we consider system of market time. Now these are the reference materials we can use. Mostly I cited here like the original works, but not like all the references. Thank you. I have to say this research, my work is actually my bursary is from Central Mathematical Research. So this whole work is supported by. Thank you. We have a few minutes for questions.
Oh, well, let's see if I understand this correctly. So you addressed two parts. So you've broken the problem down into two pieces. An integral over time domain and an integral over space domain. Now, in the time domain, your integrals will all suffer an infrared divergence, because you get a 1 over k if you choose a low enough k. Your spatial domain integrals will all suffer an infrared, sorry, will all suffer an ultraviolet divergence, because as your wave number increases, you just get an infinite energy density. So all you're saying is, if you cut out the middle section and do your calculation there, then everything is consistent. So my question is, you've done some approximations over here, and you've used a few. You used the Holder inequality there a few times. Now the Holder inequality doesn't care about the actual internal structure of the function that you're squaring and taking 1 over p through and so on. So that doesn't tell you how far you can push the bounds on the upper bound and the lower bound in that interval. Now you, at the end of your talk, you said you want to make the interval, so the interval smaller, but surely you'd be trying to make it wider. So what are the maximum bounds that you can put on that interval if you try to push it as far as possible without losing the correspondence between Lori and Kolmogorov matching?
Yes. Now, if I understood the question correctly, now the whole thing lies in it, and so what I should do over here is, like, to widen the interval K1, K2, what I should do is I should push up and then push this thing.
But how far can you do that before you lose the correspondence? Because in the math that you've written down, it doesn't show a sensitivity to to the wave modes except in the integrals. But the proofs that you used in the lemmas were statements on the bounds on simply the sums of the integrals. Now the question is, if your correspondence only works within the interval, how wide can you make that interval before you lose?
Yes, what I'm saying is,
I don't think it was totally clear to me how wide you can push.
Yeah, actually this is the widest I can push.
That's the widest.
And then I at some point thinking that this is actually an absolute bound, absolute lower bound, and this one is absolute upper bound. As you say here, things are like the bounds over here, K1 and K2. Am I using too much? Yeah. Like say, seeing as this is like constant, this is also constant. Therefore, to change this one, you need to change it right over here. And then this one is also constant. So you can't do anything. So now the problem with this one is, as you said, we are using estimates like current inequality, order inequality. And the question is how optimal inequalities are they? So the whole thing comes out of the inequalities we used in the code. Any other questions, comments? Thank you. Are there any extensions to what you're doing now? Yes, there is. Currently, I'm busy with. Now, I actually like beginning this one. I actually done this one, not in the in the sense of Turbulent, but like from the point of just enjoying the stochastic MHD equations with as much complexity. And that's what I did. And partially this one on the way, the most part. And the next step is to go from this to this way. I mean, we assume Kolmogorov's spectral, like Kolmogorov's theory, and then try to generate certain smooth regularities. Thank you. Any other comments, questions? Thank you very much. This is